A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. Find the rate of change of the radius when the balloon's radius is 30 centimeters. Okay, so if we look at the guidelines, or sort of the general approach to solving these related rates word problems. Now, there's a lot of variation in terms of the specific details, but the general approach is pretty much universal. So what are we working with here? What quantities are we working with, and what rates of change do we either know or need to know? So a spherical balloon is inflated with gas. Okay, so that's telling us we're looking at volume. And we're also looking at the radius. Okay, so we have the geometric shape is the sphere, and we have a formula that relates volume and radius. So the volume of a sphere is equal to 4/3 pi times the radius cubed. Okay, so now we've related the quantities. What we have to do is relate the rates of change. Okay, so this is our formula, this is our relationship between the quantities we're working with. Now we need to relate the rates of change. So this is why these problems are called related rates problems. So what we're going to do is take the derivative implicitly of both sides of the equation. And we'll take the derivative with respect to time because we're going per minute. Okay, so if we take the derivative with respect to time of v would be dv over dt. That's the change in volume with respect to time. Let's put the equal sign here. Okay, and now we have the derivative of the right-hand side. So 4/3, that's a constant. Pi, that's a constant. And the derivative of the r cubed, that would be 3r squared times dr over dt. Okay, so now we've related the rates of change. So the first equation in red is a relationship between v and r, and the equation in blue is a relationship between dv dt, dr dt, and r. Okay, so we've identified the given quantities and the quantities to be determined. We've written an equation involving the variables. That's what we have in red, whose rates of change we either know or need to know. We took the derivative using the chain rule and implicit differentiation. And now, once we have the derivative, has to come first. Once we have the derivatives, or the rates of change, now we could plug in the given values. So we're given dv dt is equal to 800. We're given r is equal to 30. And dr dt, the rate of change of the radius, that is what we're looking for. Okay, so this is what we're working with. All right, let's get this out of the way. Okay, so dv dt, that is 800, equals 4/3 times pi times 3 times the radius squared. So that's 30 squared, or 900, times dr dt. And that's what we're looking for. We're looking for the dr dt. All right, so we can move everything to the left and isolate the dr dt. So we have 800 equals, the 3's cancel. 4 times 900 is 3600. Dr dt. All right, looks good. So we could divide both sides by 3600 pi, and we have isolated or solved for the dr dt. 3600 pi equals and finally, if we do a little simplifying here, 800 and the 3600, well, the zeros cancel, so that's 8 over 36, or 2 over 9. So 2 over 9 pi. Or we could put this into a calculator if you need to. You could round this to a few decimal places. But remember, this is at a specific instant, a specific moment in time, at the exact instant that the radius is 30. The rate of change of the radius is 2 over 9 pi. And actually, let's be more specific. 2 over 9 pi what? Well, the radius is measured in centimeters, and time is measured in minutes. So let's be more specific and say 2 over 9 pi centimeters per minute, because it is a rate of change. Okay, so it's really important that we first take the derivative, which we did here, before plugging in any values, because as soon as we plug in values, we're stopping time. Okay, that does it for this one.